Hi there, Lucia. How are you? Welcome to the stream. Today we're going to be doing the weekly contest 467. Did you do it? Think not. Okay, so maybe you can do it with me here. Let's get started. Then usually do the weeklies. Oh, that's okay. Here's the link to Q1. Earliest time to finish one task. You're given to the integer array tasks where tasks of I. So it's the start time and t units of time to finish. Return the earliest time at which at least one task is finished. Okay, so with the input we can calculate the finish time, which is the sum of the two numbers, and we want the minimum, right? It's not, this might be one of the easiest tasks I've seen ever on LeetCode. Right? There is not much to it, to be honest. Didn't even look at the constraints. Haha, cool. Yeah. Yeah, I really don't have much to say for this one. Kind of silly. I don't know why they chose such a silly problem. No need to even handle the empty case. Yeah, but if there was an empty case, then they would have to specify what to return, right? Because there wouldn't be. So I assume there wasn't. Usually, empty input is not an option. But if it were, they would have to specify what to do in that case, what to return. Anyways, let's move on to Q2. Here's the link. Maximize sum of at most k distinct elements. You're given a positive integer array nums and an integer k. Choose at most k elements from nums so that their sum is maximized. However, the chosen numbers must be distinct. Return the array containing the chosen numbers in strictly descending order. Okay, so this in Python it can be solved with a function that's called nlargest, which is part of the heap module. So we want the k largest elements of the set of nums, right? Because we want them to be distinct. And this is all there is to it, I think. And it already returns them in strictly descending order, so it's all so yeah, there's not much to say. The only thing, so nlargest internally uses a heap. So in this case, it would be a mean heap, right? Because you would be, the idea is that you go over the elements of the set, you add them to the heap, and whenever you exceed the size of k, right? When you have k plus 1, you remove the smallest one, right? Because the smallest one is not going to be part of the top k, of the largest k. So so in a min heap you can remove the min element in logarithmic time. So you're adding elements in logarithmic time. You're removing the minimum in logarithmic time. So that's fast. And that is the case. But notice that if k is near the size of nums, you can just sort, right? Well, the size of the set, right, of the number of distinct elements, you can just sort. Here, I guess you're guaranteed to have, or no. Well, I think if k is greater than the size of the set, then it will just return the as many elements as there are. Well, here for example 3, k is 6, but there are only 2 distinct elements, so you return those and this works, right? So yeah, so it already handles that. So it's kind of weird that they kind of wrote this problem for Python, right? For n largest. But yeah, so in C++ you would use a priority queue, I think it's called. Anyways, let's move on. So far don't have much to say about these problems. This one is a little harder, I think, I hope. Subsequence sum after capping elements. So you're given an integer array nums of size n and a positive integer k. An array capped by value x is obtained by replacing every element by the minimum between nums of I and x, right? So that means that if it is less than or equal to x, it's you don't change it, right? But if it is greater than x, x is like the cap is the limit. So if you have anything greater than x, then it gets capped to x, right? So that's the idea. So you're asked, so for each x from 1 to n inclusive, determine whether it is possible to choose a subsequence from the array capped by x such that the sum of the chosen elements is exactly k. Yeah, so okay. Well, and then size, the number of numbers is up to 4,000. So that means that we can do something, and k is up to 4,000. So we could do something that is the product of these two numbers, is quadratic. Okay, so notice that when you consider the capped array, well, if you consider an array and this is the classical problem, subset sum, right? You want to know if there is a subset that sums exactly k, right? And so there is a standard DP algorithm to find that out. But here there is a catch, right? Because you have to do it with the capped values. But maybe if we can go, so remember that we can do an algorithm that is the product of these things, right? So if we know the value of x, we know that we can process the elements that are less than or equal to x, right? And do our usual DP to know the subset, to solve the subset sum. And then for the numbers that are greater, we know that all of them are going to be equal to x. So we could try searching for, let me write this down. So let's say that we have processed all the numbers that are less than or equal to. So we fixed an x, right? Remember this is a usual problem solving technique, right? Whenever you have variables, that you have things that can change, start thinking what happens if I fix something, if I guess, what if I know x, right? And what if I know x, and what if I have the usual array, let's call it can, that tells us, so true means that there is a subset that adds to 0, right? The empty set, and then for 1 we have, let's say it's false, and so on, and this is k, right? So let's say that we know that we have computed this, and we know for each number if there is a subset that adds up to that number or not, right? So how do we deal with the fact that, so we know that there are some number, let's call them q, some number of values that are going to be capped to x, right? So we want to know if there is a subset that adds to that. Well, so one option, so if k is true, then we're done, right? There's already a subset without taking into account the extra x values. We already have a subset that adds to k, so we're done, right? But otherwise, we can consider if we say, let's say here, k minus x, if k minus x is true, then, and we know that we have one x extra, at least one extra x, and this is true, then we know we can add up to x, right? Because what does this mean? This means that there is some subset that adds to k minus x, right? And then we add the extra x, and we get to k. So that means that we found, and so on. And we can, and if this is false, then we can keep trying k minus 2x. We can keep trying to see if all those x's that we have, we can try with 0 of them, with 1, with 2, so on, up to q of them. And if any of those are possible, then we found the subset, right? And that's going to be fast enough, because let's see. So we want to, well, we're going to keep them sorted. We're going to keep the numbers sorted, right? In order to do this thing of processing all the numbers that are less than or equal to our current x, right? And then we want to have this can Boolean array, right, that tells us whether there is a subset that adds up to all the numbers up to k inclusive. And initially we know that 0, we can add up to 0, right? And then we're gonna consider all the x's from 1 to n inclusive, right? And we want to, first of all, we want to make sure that we process all the numbers that are less than or equal to. So we're going to keep track of the numbers that we have processed so far, right? This is like a 2-pointer kind of pattern, right? So while this is less than n and nums of I is less than or equal to x, that means that we have to process it, right? And then we're going to increment it. And what does it mean to process it? Well, we do the standard DP, right? Remember that if we do the DP for subset sum in place, we want to go from higher to smaller, right? So the sum can go from k up to so nums of I minus 1. So, and here we want to basically say that if we can do s if we can do s minus nums of I, right? But be careful because it has to be minus 1, right? Because we want to go up to nums of I inclusive, right? Because when the sum is nums of I, this is going to be 0, right? But if it's nums of I minus 1, then it will be negative, and we don't want that, right? That would be so. Yeah, by the way, this assumes that the numbers are all positive, right? Otherwise. Okay, so yeah, so now we have updated our can array. So now we want to start trying with the number of x's, the number of extra x's that we have, right? So these are going to be so initially our current our target sum, our current sum, or is going to be k, right? And we want to repeat this. So there are n minus I extra numbers that will be capped to x, right? But we want to do this one more time than that, because initially, because initially we had 0 x's, right? So that's why, so we have, for example, if there were 1 extra x, we would like to try 0 x's and 1 x's, so that would be 2 times, right? So here we want to see if if we can make this sum, then that means that here maybe we can initialize to all to false, right? And if we found that we can make this sum, then we do res of x minus 1 equals true, and we break, right? Otherwise, we want to subtract x, but it could be that that it becomes negative, right? So we just that's another way to terminate, right? And I think that's it, right? Yep. Cool. Runs in 3.5 seconds. Yeah, I don't know if this can be done faster. Nice, thank you. All right, so yeah, so here the idea is that we just deal with the extra x's separately, right? By subtracting them from K, right? And checking our subset sum DP array. All right. So let's move on to Q4. Number of stable subsequences. So you're given an integer array nums. Subsequence is stable if it does not contain 3 consecutive elements with the same parity when the subsequence is read in order. Consecutive inside the subsequence. Okay. Return the number of stable subsequences. Well, since the number is too large, return it mod the usual mod. Let's write it down here so that we don't forget. I always want to have a constant with that. And here, well, the size is 10 to the 5. But yeah, this is standard DP, right? Because if we are doing a DP, right, and we are so remember that when you do DP, you can have you can take it or leave it, right? When you're creating the subsequence, you can, for each element, you consider each element and you can take it, you can make it part of the subsequence or not. Those are the two options. Then so here, if you take it, you have to make sure that it doesn't form it is not the third element of 3 consecutive elements with the same parity, right? So how can you know that? Well, you can remember the parity of the last 2 elements that you've added before, right? You don't care about what the values are, just the parity, right? That's gonna reduce the number of subproblems, and so with that information, you can say you can make sure that when you add it, you're not violating the condition, right? So the standard way of doing this with caching, right, with top-down DP would be just so we are counting, right, and we are considering the ith element, and we have the previous parity, right, let's say that it's -1 for when you don't have a previous element, and the previous of the previous element, right? So when we get to the base case, when we get to the end, we don't have more elements to consider, then make sure, so here it says that you have to count well, it doesn't say, right? But I think you don't have to count the empty subsequence. So that means that if b is -1, which means that we haven't added any elements, then it's 0, otherwise it's 1, right? And then we have always the option of not adding this element, right? And nothing changes. But we also want to consider the case where we are adding this element. So in that case, so it doesn't have to be true that this is the case, right? If that's not the case, then we can notice that this works out nicely, because when P or PP is not is -1, then it automatically is going to work, right? Because it's not going to be true that they are both equal to this, which is going to be a number of the parity, right? It's going to be 0 or 1, right? So -1, any number different than 0 and 1 is going to work to represent the absence of a value, right? So here we want to so now the previous one is going to be the current one, and this is going to be the previous of the previous one, and we want to mod it, and we return it, right? And here, remember that when we want to do this cache clear, and this is it, I think. Cool. Yes. So that's yeah. So it's just db. But notice that it takes 4.3 seconds to run. This was standard. Yeah. Yeah, it takes 4.3 seconds. So one thing that I recommend people who want to like the simple code, yeah, thank you. So another way, so one thing that I recommend is to learn to do this also in bottom-up DP, right? Because it's faster. I'm gonna prove it to you, because here, remember, it runs in 4.3 for a little over 4 seconds. Now we're going to do it bottom up, and also if sometimes there are harder problems, more advanced DP problems that require optimizations that can only be done bottom up. So that way. So if you get used to doing DP bottom up, I mean, it's a little bit harder sometimes to understand, especially if you're not used to it, because when you do it bottom up, you have to you have to make sure you have to care in which order the values get calculated. Here with the recursion, the order just gets solved by the computer, right? Anyway, so here let's do, so remember that we only care about we're at I, and we care about the subproblem at I plus 1, right? So that means that we don't need to have we don't need to have that variable as part of the table that we're going to be filling, right? So we just have to have the other two parameters, right? So, and remember, we need 3 values, right? Because we want 0, 1 for the parity, the reminder when divided by 2, but we also want a special value. In this case, it's going to be 2 to specify the absence of a value, right? And so, and here, remember that when so only when the first one, the first one is going to be the previous one, and the second one is going to be the previous of the previous one, right? So if the previous one is 2, that means that they are both absent, right? And in that case, we want to say, okay, so if they're both absent, then there are 0 subsequences here. Whereas in all the other base cases that are valid, we want 1. So this is another difficulty sometimes when doing the DP bottom up, that you have to initialize the base cases. I mean, it's similar to what we do when we do the recursion, but you have to think about it a little differently, maybe. And here we want to go over the numbers. We want to calculate a new of this, right? So we want to calculate. We're going to calculate the new table, and then we're going to update it in the end. And here we want to consider all the values, right? Those are all the states. And so here we have the case where the new one is the one that we want to fill, right? So here, this is the case where we skip it, right? And then here, if we're not in this case, then we also want to consider this case where here the previous one is going to be x mod 2, and then this is going to be this, and then we mod, and this is so initially initially we don't have a previous one, and we don't have a previous of a previous one. So that's what 2 means. I guess you could use -1 if you liked it, but that's okay. All right, so let's see how fast this is. All right, so yeah, so it's half the time, right? 2.2, almost half. And it uses less memory, right? Because remember this we're saving only we're not saving the variable n in our table, right? Since we only care about the previous table, we're not saving it, so then the memory is just a constant, right? Because it depends on, well, it depends on the parity, right? So it's 9, it has 9 elements here. You can consider it constant time, constant space. So yes, this is, so do you see how this is in a sense it's the same thing, right? It's kind of mechanical to translate from one to the other. It's like basically you do the for loops to go over all the possible sub problems, and then this part is pretty much the same that we had in the recursion, right? But instead of, yeah, you write access to this table, right? But instead of calling recursively, but it is the same idea. So you should be able to translate it pretty easily if you once you understand it, right? Cool. So I think that's it. I don't have sorry if I don't have more for this contest. It's not my fault. I think the Q1 and Q2 were a joke. I don't know what happened with LeetCode, but they gotta do better. Especially because many people, so this generates a pretty bad experience for many people, because many people will solve Q1 and Q2 very quickly, and then maybe Q3 is well actually Q3 is harder than Q4. I think is much, so Q4 is much more standard. I mean, Q3 is also a little standard, but you still have to work a little bit and have this idea of dealing with the spare x's, right? At least you have to be creative in that. But yeah, I feel like many people maybe solve Q1 and Q2 very quickly in the first few minutes, and then they got stuck on Q3, and that was the end of their contest. They struggled and they couldn't solve Q3, and that's not a good experience, right? You don't want to have such a big jump in difficulty, right? Anyways, so yeah, that's all I have for now. So thanks for watching, and see you on the next one. Bye bye.